Hello folks, this is a short tutorial on the use of the surface force density that is available in the Catia V5 when you do finite element calculations on it. When you go to the generative structure analysis, which is the FEA module within Catia V5, also referred to as the Affini program, and you click on the loads toolbar, you get uh, the following set of loads that you can apply in Catia, and the specific one that we are interested in is this fourth one from the left side, which is actually a set of four icons. So if you expand this thing, you get the force densities toolbar, and the one on the left is line force density. The one that we're going to be discussing in this tutorial is the surface force density, which is the second one from the left. And then third one from the left is the volume force density, and the final one is just force density. This particular tutorial deals with the surface force density, which is a fancy version of essentially traction, quote unquote, pressure applied on a surface. Now keep in mind, pressure is perpendicular, normal to the surface, but surface force density expands the capabilities and the abilities of working with pressure, not necessarily normal to the face. Probably more appropriately should be referred to as traction. Now, there is a description of when do we need to apply this surface force density. It's actually a for convenience, because it probably can be done in different other ways without using this particular icon. But I'm not going to do it in the context of what's described here. I'll do it for a simple problem. Incidentally, this particular tutorial is parallel to the one that you see at the very bottom, which is applied to the abacus, because the same feature is available in abacus. Abacus CA. Now, when you click on the surface force density, you get a dialog box. You have the ability to select your surface, of course. It can be a curved surface, it doesn't have to be flat. You can create your coordinate system, and then you put down essentially the components of pressure. This is a bad way of saying it. Components of pressure in different directions. This is just an example. Here's the help, which is not very helpful. At the very bottom, I circled this date here, 2003. This is coming from the help back in 2003. The reason I mention this is that Catia V5 has been around for roughly 25 years, and the FEA module in it, quote unquote, Affini program, has been also in it for the past 25 years. And no major changes have been made to Catia or its FEA solver. Now, the example that I'm going to be doing here is a geometry like that. Left end of this part is clamped, and the right end is subjected to a surface force density of 200 psi in the downward direction. The reason I do this thing is that you can view that as a cantilever being clamped at one end and point loaded, for example, at the right end, because we have an analytical expression for that from elementary strength of material. We want to compare our results with it. The dimensions are given here, all in inches, and the Young's modulus is 29 million psi, basically. This is the default value for steel in Catia program. And the formula that I was referring to from strength of material is FLQ over 3EI. So F is the point load, which is going to be that traction times this area. Right here, you can see that. The traction times the area, which is 1 times 0.5. And then plug it in, and you're going to get 0.0931 inches. So we're going to be comparing our results with this particular number. All right, let's go ahead and do that. We start with a part file. All right, on the vertical plane, I will sketch that cross section, which essentially is a rectangle. This is 1 inch, the height, and the width of the beam is 0.5. All right, exit. and we're going to pad it by 15 inches. Okay, let's apply material to that. Here's apply material. You click on it. You select the metals tab, and we're going to go to steel. Select the part, and then say OK. And we can check to see what value it's using. If you double click on steel here and select the analysis tab, you see that the value of the Young's modulus is 29.1 times 10 to the 6 psi, which is exactly what I have in that expression. Now, this is done, so we're going to go to generative structure analysis. Catia automatically meshes it, and the type of element is going to be, of course, tetrahedral, because that's the only thing available in the Alfini program. Well, unless you want to go to the advanced meshing tool and you do some fancy stuff. But the size of it, I'm going to make it a little bit smaller here, maybe I don't know, 0.5 parabolic type, and you can look at it just so that you have an idea how it looks like. Let me change the rendering here to with lines. So basically a parabolic of this type. Let me deactivate the mesh and we proceed with the rest of the problem. All right, so we have this end is clamped, so you go to restraints toolbar. Here is a clamp, and the other end is subjected to a surface force density. And notice that here is the toolbar that I had in the slide. Turn this thing around, and there is the fourth set of two icons from the left. So there is the force density. These are things that I refer to here, okay? And the specific one that you want is the surface force density. You click on it and you select that face, and we want things to be in the negative Z direction. The reason it has the right value here is because I already made a practice run, and I put down minus 200 psi here. Now, you can change the coordinate system, but I'm happy with the global in the negative direction, negative Z direction, global 200 psi. We say OK. And that's pretty much it. So we can run it now. All right, good. So if you look at the displacement right there, notice that this is the magnitude of the displacement. Not only displacement is that direction, but the magnitude of it. In other words, square root of displacement x squared plus displacement y squared plus displacement z squared added up. That's why this number may not, in your case, depending on what the size of the mesh is, this number may not be uh, quite what you're looking for. Because this is not the displacement in that direction. If you want to get that, double click on this, go to more, and then say for component, just give me the component in the third direction. Didn't change that much. So the moral story is that if you look at it, displacement in that direction is very close. It's 0.093. Okay. Anyway, so which matches quite well with this percentage-wise with this number. Now notice that what I could have done, I mean, it's not what I want to do, but if you could, for example, gone to this, just hypothetically, to this load here, where is this? Right there, and modified that. For example, you also want a pressure applied to that face. So you put down let's say pressure of 100 psi, okay? 100 psi into that phase, of course, minus 200 down, and then you can run. Notice that it gives you actually, what I did is here, let me go double click on that. I put the wrong start here, 0, down 100. Now it's going to have a component into 200 psi downward and 100 psi into that phase. And then you can run it. So you can see that this can be useful, but there are other ways of doing the problem too. Good luck.